Right, we are discussing the vacuum solution to the Friedmann equations. And maybe I should write the vacuum Friedmann equations because we will need it again. So we call, in general, there are two Friedmann equations, but for the vacuum case, one of them is a consequence of the other. So we have to deal only with one of them, and that's it. So it's the first order differential equation for the scale factor A, and we have on the other side the zero because the mass density is zero. Yeah? Here we have the mu in general, but in vacuum we have the zero here. And I already began with the discussion for, or actually I finished already the discussion for lambda equals 0. So we had to distinguish three cases. K equal plus 1, there we had no solution. Then we had K equals 0, well this could have been guessed already, that here we would get Minkowski space. And we get it with ordinary slices associated with inertial systems. And for K equal minus 1, we also got Minkowski, but with a different slicing and not the whole Minkowski space, only a part of it, with a so-called Milne slicing or Milne coordinates. Okay, so the only solution, the only vacuum solution with lambda equals 0 is Minkowski space. Here it comes in two different versions, but it's the only space-time which satisfies this equation. And then we finished already partly, but not fully, the case lambda bigger than 0. There we had for K equal plus 1, so the zeta universe. The zeta universe, yeah, K equal plus 1 means the spatial sections are three-dimensional spheres. So let me write here spherical slicing. And the picture, that's important, we will come back to this in a minute. The picture is that the zeta universe can be embedded into five-dimensional Minkowski space. So we invent a fifth spatial coordinate. So we have now five-dimensional Minkowski space-time, and the zeta universe is a hyperboloid. These are the slices. The slices are three spheres. Yeah, each slice is a three-sphere, and then there's a time coordinate running in this direction. So these are the standard observers, these lines. So it's a universe which contracts, reaches a minimum radius, and then re-expands. So this was K equal plus 1. And then we also did K equals 0. And what we got was again the zeta, but this time with a flat slicing. K equals 0 means spatially flat. So how can you slice the hyperboloid in a flat way? We can do it by restricting to this half of Minkowski, of the zeta space, and then these are the slices. So these are lines in the picture. Yeah, actually these are, so they come down here, reach here a minimum, and then they go up on the other side. These slices are flat three spaces. So in the picture they are represented by lines, but actually they are three-dimensional. Yeah, they are three-dimensional Euclidean spaces. And this coordinate system which we get by solving this equation with K equals 0 covers only half of the zeta space-time. So here we have, in the full, the zeta universe is a light-like hypersurface, and this light-like hypersurface bounds this region which is covered by this slicing. So, and the third case, which we still have to do, which I haven't done yet, is K equal minus 1. So let's see what we get for K equal minus 1. So that's a differential equation. Lambda is positive and K is minus 1. So we have to solve the differential equation. 0 is minus c squared plus a prime squared minus lambda over 3 c squared a squared. Let me see, this gives a differential equation for A. If I take this to the other side, or no, the other two terms to the other side, then I get c squared 1 plus lambda third a squared. And this is just a shorthand for dA by dt squared. So I can take all expressions which involve the a on one side and the other ones which involve the t on the other side, and then I got dA over root 1 plus lambda over 3a squared, and on the other side I get plus or minus, because I've taken the square root, c dt. So that's the integral we have to calculate. And well, if you have one, lambda is positive, so something is added to the one, and then the standard substitution is that you write for this expression sinh squared, right? That's a standard substitution for such an integral. So we write lambda over 3 a squared should be sinh squared of a new integration variable u. This means root lambda over 3, and that's positive. Here in the case lambda bigger than 0 is the sinh. This means dA is root 3 over lambda cos u du. And if I insert this into our differential equation, then I get dA is root of 3 over lambda cos u du. And here I have root of 1 plus sinh squared. And on the other side, plus or minus dt. And you see 1 plus sinh squared is cos squared. So I can easily integrate this. So I have u is plus or minus root over 3t. You may put an integration constant here if you like, but it is yes, it's true. Okay, so what we're interested in is the scale factor. A of t is what? A of t is root 3 over lambda sinh u, and this plus or minus root 3 over lambda sinh root lambda over 3 ct. So this is a universe with a big bang in quotation marks. The t starts at a finite time. If I plot the scale factor, always keep in mind the scale factor must be positive. Only positive values for a are allowed. So if you choose the plus sign, then it is just this part of the sinh function, right? It is this part of the sinh function. So it starts with a singularity where a is 0, and then it goes up to that's not a nice picture. It's like it's like this, right? And here we have the negative part, which cannot be used here. You may also use a minus sign, then you get the other branch, and this is just the time reflected situation of the solution with a plus sign. So there are two separate solutions. They are not connected with each other. One with a plus, one with a minus, and one is just the time reversed version of the other. So what is this? What we get here? The metric is then what? The metric is minus c squared dt squared plus the scale factor squared. And the scale factor squared is 3 over lambda sinh squared root lambda over 3 ct. And then the spatial part, the eta squared, that's the solution with k equal minus 1. So I have 1 plus eta squared here. The omega squared. And that's it. And now we discuss what is this. You study this metric. You're already expecting that you have found a new metric. You've learned something new, but it turns out to be again the zeta space. The zeta space in the third coordinate version. So it's again part, not the whole space. Again, part of the zeta. So if you do all the, I will not calculate this on the board. I just tell you how it is embedded. So here we have these light-like hypersurfaces. Yeah. So if you cut through the hyperboloid with a three-dimensional hyperplane which goes through the origin, then you get something on the hyperboloid which is straight. Yeah? The hyperboloid is just the ordinary hyperboloid in 2 dimensions is ruled by straight lines. Yeah? And these are the ruling these are the ruling lines, 2 of them. And the universe, which is covered by this slicing, sits in here. So these are the spaces of the hyperbolic spaces. Here, these spaces. Yeah. So each slice is a 3-dimensional hyperbolic space, constant space of constant negative curvature. These are the standard observers in this representation. And of course, it can cover also this here, then it's a space-time with a minus sign. Here's a time reverse situation. This covers the lower part. So this particular slicing of de Sitter space-time covers a region which sits in the full de Sitter space in a way very similar to the Milne universe in the Minkowski space-time. Yeah? So you have these light-like boundaries. So all the word lines start at one point. So that's the singularity here, right? The scale factor becomes 0 at this point. This corresponds to this point where all the standard observers come together, but it is not a true singularity, not a curvature singularity. The full de Sitter space is perfectly regular everywhere. Yeah, there are no coordinate singularities. Also, the density is not infinite at this point because it's a vacuum solution. The density is 0. Yeah? So in this sense, it's not a Big Bang. It's quite analogous to the singularity of the Milne universe. It's a point where all the standard observers come together. So it's the singularity of the slicing, not of the space-time. Okay, so we see the case lambda equals lambda bigger than 0 yields 3 different versions of de Sitter space, 3 different slicings for de Sitter space, but the space-time itself is always the same. It's the only solution. The only solution of this equation with lambda bigger than 0 gives us de Sitter space-time, or part of it. Okay, and now let's complete this with we will come back to de Sitter space frequently, because as I said already, it is important as a limiting space-time for universes with matter. And we have to do the third case. The third case is lambda smaller than 0. I will do this a little bit quicker because it's not so interesting, in view of applications to cosmology at least. So let's check the 3 cases again. K equal plus 1, then we have to solve the differential equation A prime square. Let's take all the other things to the other side. If K is plus 1, I get a minus C squared on the other side, and I get plus lambda over 3 C squared A squared. Lambda is negative, so this whole thing is negative. So it can never be the square of a real quantity, right? So there's no solution. Hopefully not. K is plus 1. I take it to the other side, so I get minus C squared, I think. I'm fairly sure that the system of equation for K equal plus 1 has no solution. Okay, let's try K equals 0. It's the same thing, but instead of this term I have a 0 now. A prime squared is just lambda over 3 C squared A squared, and lambda is smaller than 0. So this is smaller than 0. Yeah, these are squares and A is non-zero, so it's really strictly bigger than 0, but strictly smaller than 0. What we have on the right-hand side, and again we have no solution. No real solution for A. And the third case, where this does give something, would be too boring otherwise. So if we do it with K equal minus 1, then we have here the other sign. So we have A prime squared is plus C squared plus lambda over 3 C squared A squared. So this is dA over root 1 plus lambda over 3 A squared is plus minus CDT. And now be careful, lambda is negative. So here's something subtracted from the 1. Yeah? And if you have such an expression, the root of 1 minus something which is positive, then the standard substitution is sine or cosine. Yeah, because 1 minus sine squared is cosine squared, and 1 minus cosine squared is sine squared. So we substitute lambda over 3a squared. This is negative, so let's put a minus sign in front of it, then it's positive. So I can substitute this by sine squared of u. So this means root of minus lambda over 3, which is real, times a is the sine of u. And if I differentiate this, I get dA is root minus 3 over lambda cosine of u du. Okay, so our differential equation becomes minus root 3 over lambda cosine u du divided by root of 1 plus lambda over 3a squared. This means 1 minus sine squared. And 1 minus sine squared is cosine squared. So again, this goes away. And here we have plus minus CDT. Any problem?
The minus don't have to be.
Oh, sorry, the minus is inside the square root, of course. Yeah. Oops. That's it. Can you read this? Okay. So if I integrate this, I get u is plus or minus root minus lambda over 3 ct. And a of t, our scale factor, was root minus 3 over lambda, the sine of this thing, the sine of u, so I get a plus minus. Yeah. The sine is, I can pull the minus sign out of the sine function. And that's the solution. So again, this has a big bang. It also has a big crunch. Yeah, we have to see where is this positive. And it's positive, well, you can choose the interval as you like. By the way, you also could add here an integration constant, so you could shift the interval as you like. Yeah? So for instance, you could also write cosine instead of sine here, just by adding here an appropriate constant so that you get a plus pi half here. Yeah, then the sine becomes a cosine. So there are many, you can shift it wherever you like, but to get something with this shape, if I plot this over t, you see this comes up, reaches the maximum, and goes down again. Yeah? So whereas this is 0, if I stick with this representation, this is 0, and this is the argument must be pi half, right? So t must be pi half divided by c times the root of minus 3 over lambda. So we have a big bang, and the universe expands. It's a universe with k equal minus 1, so with hyperbolic slices. So the universe expands, and then it recollapses, and we get a big crunch. And the metric, I should write the metric. The metric is this here. Now plus the scale factor squared, this is minus 3 over lambda, but keep in mind lambda is negative, so here's something which is positive. And the sine squared root minus lambda over 3 ct. And the spatial part, we have again k equal minus 1, so it's the eta squared over 1 plus eta squared the omega squared. This spacetime is what is called anti-de Sitter spacetime, or more precisely, it is part of anti-de Sitter spacetime. So this is anti-de Sitter spacetime, which is often abbreviated ADS. Yeah? ADS spacetime means anti-de Sitter spacetime. And what is anti-de Sitter spacetime? The full anti-de Sitter spacetime is again a kind of hyperboloid embedded into a higher dimensional space. So the full de Sitter spacetime is the hyperboloid, hyperboloid, hyperboloid. Well, in the 5-dimensional space, x squared plus 1 squared plus z squared minus w squared minus v squared is minus lambda over 3. And this sits in a 5-dimensional space with a pseudo-Riemannian metric, not with a Minkowski metric, and not with a positive definite metric, but with a different signature, namely where I have the same combination of signs as here. So the first 3 come with a plus, but the other 2 come both with a minus. Yeah? So remember, the zeta spacetime was embedded into a 5-dimensional Minkowski spacetime. So we had something which is 4-dimensional with Lorentzian signature, and we added a 5th dimension which was space-like. So we get 5-dimensional Minkowski spacetime. And then we considered this hyperboloid, and this gave us the zeta spacetime. Here we have something which is 4-dimensional with Minkowski signature, and we add a 5th dimension, but it's a time-like dimension. Yeah? So we have now, here I should point to this equation. So we have 2 minus signs and 3 plus signs. So, and this has the effect that the hyperboloid, because I have the different signs, are now situated in a different way. It's again a kind of a hyperboloid, but it is, one usually draws it horizontally because the time coordinate goes up. Yeah, so here we had a slicing. Here we had a slicing. These were 3 spheres, and this was a real line. So the topology is of this thing is a 3-sphere. Let me denote it in this way, as mathematicians often do. That's a 3-sphere, and this is a real line. So the zeta space has topology as 3 times R. This here has 3-dimensional infinitely extended spaces in the horizontal direction, and the time-like direction is rolled up. So this has topology. The 3 spaces are topologically R3. Yeah, they are not flat Euclidean spaces, but they have the topology R3, and then the 4th dimension of the hyperboloid is rolled up into a circle, and this is a time-like dimension. So we have here closed time-like curves in the de Sitter spacetime. Yeah? So if you are on, this is a world line. It's an allowed world line for an observer in the full I said de Sitter, but I meant anti-de Sitter, in the anti-de Sitter spacetime. So if you move on this world line, you come back to the same event where you have started. So then you can kill your grandfather and he will never be born, and you know these stories, yeah? If you have closed time-like curves. So for this reason, most people think at least the full anti-de Sitter space, this hyperboloid, is topology. This full anti-de Sitter space is, with this topology, is probably not physically relevant. But what may be relevant, at least one could speculate, is a universal covering of this, where you unwrap this S1. Yeah, and S1 is something like that. And you can use a universal covering manifold, which is a spiral which goes up. Yeah, and the local geometry everywhere is the same, which you get from the projection. That's what one calls the universal covering. So if you consider the covering of this rolled up dimension, then you get something where you do not have any closed time-like curves anymore. And this universal covering space of anti-de Sitter might be, well, not totally unrealistic as a space-time model. I should explain you how this Robertson-Walker universe, which we constructed here, is situated inside the hyperboloid. It's not the full hyperboloid, it's only part of it. And it is actually, well, if you slice again, in the way as we also did for one of the slicings with the de Sitter space, then what is covered is this region here with these hyperboloids. Yeah, so here is a Big Bang, if you allow me to say so. Then here's a standard observer start, and they meet again in the mirror point of this on the other side, on the back side. Yeah, so they start in this point and come back in the point on the back. So they start here and they come back all together here. So that's how this this particular slicing, this particular Robertson-Walker universe is situated inside anti-de Sitter spacetime. Well, it's geometrically quite intriguing, and you can play around with it for quite some while. But I will not spend any more time with anti-de Sitter, because I do not believe that it is relevant, at least not in view of cosmology. Actually, anti-de Sitter has a very strong lobby among the string theorists. String theorists love anti-de Sitter. And the reason is that a while ago there was a formal analogy discovered between properties of anti-de Sitter and some so-called conformal field theories, where people has nothing to do with relativity, but they do conformal field theory. So they discover, they study a certain type of field theory which really has applications for things you can build in the lab. And there was a formal analogy discovered between this class of conformal field theory and anti-de Sitter spacetime. And they are now doing calculations just on the paper in anti-de Sitter spacetime in order to learn something about conformal field theory. That's this famous ADS-CFT correspondence, which is very, very popular and very, very fashionable at the moment. But I really want to emphasize that this does not mean that anti-de Sitter spacetime has anything to do with our real world. Yeah? And that's not the claim. Also, the string theorists do not claim this. So it is just a mathematical tool in order to calculate things. As far as our real universe is concerned, we are pretty sure that the cosmological constant is positive. And this is a spacetime with a negative cosmological constant. And for this reason, I believe, in view of cosmology, anti-de Sitter is not relevant.
The first question is, those people doing ADS-CFT correspondence, they're not concerned with real values for lambda and A at all, so they do just mathematics.
Right, yes. That's, they do it in view of applications to physics, but not in view of applications to our real universe, yeah? Of course, conformal field theories have something to do with physics.
Yeah.
So I'm not saying that it is pure mathematics. Yeah, it certainly has something to do with physics, but I do not think that it has any relevance in view of cosmology. And actually, most books on cosmology have a long section on de Sitter. So, for instance, Mukhanov and Ryder and others. But I just looked it up yesterday. Mukhanov and Ryder don't even mention anti-de Sitter. Yeah, so because they apparently also believe that this is not particularly relevant. Okay.
But these are solutions which are, in any case, could be only limits.
Yes.
So it might be the case that lambda is now positive, but then it becomes negative.
Yeah, but, well, limit in the sense of that you really approach this asymptotically. And if you have a sequence of space-time models where lambda is positive, then you cannot reach in the limit something where lambda is negative. Right? You could reach a limit where lambda is 0, but not where it is negative.
But can't it become then the negative of the becoming 0?
Yeah, but then it would not be an asymptotic limit of a family of solutions with positive lambda. And that's what we are interested in. Yeah? So, okay. By the way, as we are talking about the cosmological constant, maybe I should remind you about the physical interpretation of the cosmological constant. Remember that a positive cosmological constant has a repelling effect, and a negative cosmological constant have a contracting effect. Yeah? So I think many of you know the Kotler spacetime, which is also known as Schwarzschild-de Sitter spacetime, where you have Schwarzschild modified by a cosmological constant. If you do it with a positive cosmological constant, then you have a point where the gravitational attraction is balanced by the repelling effect of the cosmological constant. And if you are farther away, then gravity is even repelling. So if you set a point, if you place a test particle close to the central object, then it will be attracted. If you place it far away, then the cosmological constant would push it away, and there's an equilibrium distance in between. So that's something you should always have in mind. A positive cosmological constant has a repelling effect, and that's what you can, what you see visualized in this picture very nicely. Yeah, that's a space-time with a cosmological constant. So the standard observers come together in the beginning, but then they are repelled from each other. Yeah, they are pushed apart. And so in this picture you see very nicely again the repelling character of the cosmological constant. Yeah, in Minkowski spacetime with lambda equals 0, of course you do not have this. Well, you could mimic this This also by coordinate effects of, well, also the Milne universe is expanding. Yeah? So in a sense, maybe I'm overdoing the interpretation. But anyway, it fits together. Yeah, it fits together with this idea that the cosmological constant has a repelling effect. Okay, so what have we learned now? So now we have discussed all cases. We have found actually all solutions to the Friedmann equations in vacuum. We have discussed all solutions. There are these 3 times 3 cases: lambda bigger than 0, smaller than 0, or equal to 0, k bigger than 0, equal to 0, or smaller than 0. And we see that we get only 3 different spacetimes: Minkowski, de Sitter, and anti-de Sitter. They come with different, in different disguise. So de Sitter, in a sense, is the mathematically richest example of the 3 because it can be sliced in any of the 3 ways. Yeah? You can slice it with k equal +1, with k equal 0, and with k equal -1. Minkowski only works with 2 cases, k equal 0 and k equal -1. Anti-de Sitter only works with k equal -1. And, well, what have these 3 spaces in common? Well, they have in common that they are spaces of constant curvature. So, Minkowski, de Sitter, and anti-de Sitter are all spaces of constant curvature. We have discussed the notion of a space of constant curvature for the 2-dimensional Euclidean case in quite some detail, then generalize to the 3-dimensional Euclidean case, and of course you can do it in any dimension with any signature. And the characteristic property, the property which really tells you that you have a space of constant curvature is that the Riemannian curvature tensor has this structure. Here's a curvature constant, and then G, how are the indices? Mu sigma. I have to begin with these, I think. G mu tau, and then the first 2. G mu nu sigma tau. And what is written here is a curvature. And in these cases, in these 3 cases we have discussed, the curvature is given by lambda over 3. Well, so for de Sitter, we have a positive curvature. Minkowski space, we have the 0. Of course, Minkowski space satisfies this with the 0 on the right-hand side. And for anti-de Sitter, we have it with a negative lambda. And, well, I don't calculate this on the board, of course. But if you plug the form of the metric into any of these forms, yeah, so you can use any coordinate representation for the space you like. You calculate the Riemann tensor, and you must reproduce this expression. So these are spaces of constant curvature, and I already mentioned that spaces of constant curvature are characterized by the fact that they have the maximum number of Killing vector fields, of symmetries. Yeah? So in 4 dimensions, the maximum number is 10. So you know Minkowski space has 10 symmetries. It has the 4 translations, the 3 boosts, and the 3 spatial rotations. 4 plus 3 plus 3 is 10, yes. So this is what one calls the Poincaré group, yeah, the symmetry group of Minkowski space. And they are analogously defined symmetry groups for de Sitter and for anti-de Sitter, also 10-dimensional, and they are called the de Sitter group and the anti-de Sitter group. Yeah? So they have maximal symmetry. That's a common feature of these spacetimes. So this was the section on the vacuum solutions to the Friedmann equations. So they just give the spaces of constant curvature in different disguise. And now I have 10 minutes. The next section would be dust solutions. So let me begin with this. Oops. If there are no questions to the vacuum cases.
I have one question.
Yeah.
Just for curiosity. Are there people calculating also something on the imaginary solutions? I mean, you can calculate anyway, but...
Okay, the question is if it is meaningful in a certain sense to consider an imaginary A. Then of course we could, where I've written no solution here in all these cases, you would get something where the A is imaginary, yeah, or complex. Yeah? Does this make sense? Well, not if we are doing Lorentzian geometry. Yeah? Not if we are considered in a matrix with Lorentzian signature. But if you allow for something which is called signature change, yeah, that you change to a different signature, then you could do this. Yeah. If this has anything to do with our real world, well, I'm not sure about this. Stephen Hawking was one of the proponents of this idea of signature change. That in the early state of our universe, the time becomes imaginary or things like that. Who has written this book? How is it called? The first book by Hawking. My goodness. A Brief History of Time. Brief History of Time. Yeah. Who has read it? Okay, you understood it? I didn't. Okay, so there's something about the imaginary time. Okay. So yes, it's not completely out of the question to discuss something like that. But in our standard theory of general relativity, we are not doing this. Yeah, we are just dealing with metrics of Lorentzian signature. So I wanted to say a few words. I won't get very fast. A few words about dust solutions. And then the third part will be perfect fluid solutions with the pressure. And the vacuum solutions we could discuss fully. Yeah, this was a full discussion of all possibilities. And for the dust solutions, I will also, at least discuss most of them. And here we have to consider. We have to consider both Friedmann equations. Yeah? So we had these equations which I called Friedmann 1 and Friedmann 2. And now I specify to the case that it has the dust. So the mu is different from 0, but the p is 0. And then the equations were 3 squared k over a squared. 3 over a squared, a prime squared minus lambda c squared. And here we had the 0 for the vacuum solutions, and now we have kappa c to the 4 mu. Where mu, we have a dust, so mu is just the rest mass density. Okay. More generally, it is an energy density, but here it is just the rest mass density. And then we have the second equation. The second equation is this here. Minus k minus 1 over c squared a prime squared minus 2. Now comes the interesting thing. Here comes the second derivative, a double prime plus lambda a squared is equal to 0. So please recall that Einstein's field equation is a second order differential equation. Yeah, a system of partial differential equations of second order for the metric. So you will expect second derivatives of the metric coefficients. And in this case, for the Robertson-Walker spacetimes, we have only one occurrence of a second derivative. More generally, if you just deal with, let's say, vacuum Einstein field equation, with the vacuum Einstein field equations, you will always see that there are certain components of the field equations which contain only first derivatives, and those which contain the second derivatives. The first group is called the constraints, because it just restricts the initial values which you can give on a hypersurface. And the second class, where the second derivatives actually occur, are called the evolution equations. And the fact that for vacuum we didn't have to consider the second Friedmann equation reflects the fact that if you just satisfy the constraints, the equation which involves only first derivatives, then the other one is automatically satisfied. Yeah? So if the constraints are satisfied, the vacuum Einstein field equation has this nice property that, as the mathematicians say, the constraints propagate. So if they are satisfied on one hypersurface, then the evolution equation makes sure that they are satisfied everywhere. And what we have done last time, when we saw that the second Friedmann equation for vacuum is not necessary, was just a particular example which demonstrated the fact that it suffices to solve the constraints for vacuum equations. And it's a little bit more complicated if you have matter. And here you see actually the equations are not independent of each other. So if I just satisfy this equation, well, first of all, why is the situation more complicated? Because now we have two variables. Yeah? In the vacuum case, with a 0 here, we had only the A. Yeah, it was just a system of equations for A and nothing else. Now we have also the mu. We have two unknown variables, A of t and mu of t. Of course, mu also can depend only on t, right? Because the left-hand side depends only on t. So it doesn't make sense to require the mu to depend on the spatial coordinates. You cannot solve the system then. So it's a second, it's two equations for two unknowns. And for this reason, it's fairly clear that we will need both equations. Yeah? And the way in which we evaluate these equations, well, there are two possibilities. First possibility would be just begin by solving F2. F2 doesn't involve the mu. It's just an equation for A. If you have found a solution for A of this equation, plug it into this equation and calculate the mu from this equation. That's one way of solving the system. It works. You could do it in this way if you like. I will do it in a different way because then it can be done quicker. What I will do is I will derive from the two equations together a conservation law, which actually has a physical interpretation, namely it's the conservation of mass. Yeah? So this relates the mu and the A by way of a conservation law. And then I solve a first order differential equation for the A, not the second order differential equation, but only the first order differential equation for A, and determine the mu from the conservation law. That's the quickest way of doing it. But I will not do this in 2 minutes, so I have to stop here, and I will continue with this next time. Okay, see you on Tuesday.